Okay, so in moments of technological frustration, it helps to remember that a computer is basically a rock. Like that's the fundamental witchcraft of computing, that no matter how complicated it is, it's basically just a complex arrangement of minerals that is animated by electricity and language. It's just a really smart rock. And the miniaturization of smart rocks, which is a trend that we call Moore's Law, has fueled decades of economic activity, the pillaging of the planet, and has given us enough raw computational power to model the climate and discover new molecules and emulate human learning. But there are limits to what rocks can do, and there are only so many rocks left to do it with. So demand for the high quality, the high purity silica sand that's used to make silicon chips is causing a global and irreversible shortage of sand. So if we expect computers to process the stupendous amounts of data that our culture now produces, and we expect them to do it sustainably, we need to fundamentally reimagine how computers are built and what a computer even is. One way is to build computers around a speculative component called a memristor, which is essentially a resistor with memory. Memristive computers could turn off and on like a light switch, and they wouldn't require the conductive layer of silicon that's necessary for traditional resistors. So no rocks required. But there is another, I think, more interesting way, and that is to use slime mold. Now, a lot of people think that slime mold is fungus. It's not. It's not a fungus. It's not an animal. But it's been misclassified many times throughout history, which has given it the Latin name mycetozoa. Myceto for fungus and zoa for animal. So you can think of it as a kind of fungal animal. In 2014, researchers discovered memristive behavior in the slime mold Fusarium polycephalum, which means that this slime mold actually behaved like a yet to be commonplace speculative next generation computing component. And in addition, even though it has no central nervous system, it's capable of kind of limited learning, which has made it the leading candidate for a new kind of biological computer, one that is not mined, but grown. In 2014, researchers placed a Fusarium on the west coast of a topographical map of the United States, and they placed a pile of oat flakes in Boston. After 5 days, the mold shot out these protoplasmic tubes, finding an efficient path towards the food. And if you've ever road tripped from Oregon to New England, you will recognize this route. It's Route 20, the longest road in the US, exactly. In 2010, the same species of slime mold independently traced a perfect copy of Japan's interconnected railroad networks. And in 2020, researchers used an algorithm based on Fusarium's behavior to trace the filaments of the cosmic web that make up the universe. So it's uncannily good at forming networks. And it also excels at certain thorny computational tasks, like solving mazes, solving computational geometry problems, and finding the shortest path between 2 points. Researchers in China showed that Fusarium is able to solve the traveling salesman problem, which is a long-standing problem in computer science that requires massive amounts of computing power. In 2006, researchers at the University of Southampton and the University of Kobe built a 6-legged robot whose movements were remotely controlled by the Fusarium slime mold, which bridged the gap between artificial and natural systems for the first time. And interestingly, the robot retreated from light, which was the slime mold expressing its natural desire for its natural habitat, which is darkness. There is an EU-funded research group called PHI Chip that works exclusively with Fusarium slime mold in the hopes of building a hybrid computing component by coating the protoplasmic tubes the slime mold creates with conductive particles to create a functional biomorphic computing device that would be sustainable, self-healing, biodegradable, self-correcting, and by some definition, alive. Professor Andrew Adamatsky, pictured here, runs that project. His lab has produced nearly 40 different prototypes of sensing and computing devices using slime mold. But unconventional computing as a discipline is actually much broader. It's a hybrid of computer science, physics, mathematics, chemistry, electronic engineering, biology, material science, and nanotechnology. And under the umbrella of unconventional computing, there are people working on solving mazes with lettuce seedlings, building plant leaf computers and fungal computers, and computers driven by the billiard ball-like collisions of particles and marbles, and even the way that hundreds of soldier crabs collide into one another as they rush from shade and sunshine on a beach. The sheer multiplicity of biological unconventional computing approaches is enough to make you think that computing is not so much an industry or a technology as a way of seeing, an interpretation of the world. So if you're looking for a computer, even if you're looking under a rock or in a root system or in a slime mold, a computer is what you'll find. And that's interesting, but it can also be a trap. The artist and critic James Bridle describes computational thinking as the unique mental disease of the 20th century, arguing that by making data processing machines, we have inadvertently reduced our world into data to be processed. As computation surrounds us, he writes, reality itself takes on the appearance of the computer and our modes of thought follow suit, which could not be good. But if we invert that approach and actually build computational systems from the Earth up to model the ways that nature processes information, we would not need to limit our thinking in this way, because rather than abusing the planet to build our systems or to fit into our systems, we could learn from and plug into the natural world's existing computational processes. Of course, nature is a lot more complex than just slime mold and lettuce seedlings, and these are just really the simplest systems that can be studied and manipulated in a lab environment. It's hard to imagine that we could ever build a computer as beautiful and as complex as the interrelation of roots and fungal mycelium in your average healthy forest, which scientists evocatively call the wood wide web. And that's something that really bears emphasizing, because as the computing industry works towards embedding artificial intelligence into every material surface around us, building the Internet of Things, at best, they're poorly emulating processes already at play beneath our feet in our gardens and in the forests around us. They're making a bad copy of the Earth, and in doing so, they're also destroying the original. So even though the alternative approach may seem really radical, it's not. In the 50s, electrical analog computing was the standard, and today we live in a digital world. Only 20 years ago, quantum computing was considered to be science fictional, and today it's being actively developed worldwide. So a similar process might and needs to unfold with biological systems if we're going to survive this century. What is unconventional today will be conventional tomorrow. Thank you.